Hey everybody. Sorry this is taking a while for me to get out. Um, I wanted to prepare in such a way that this will hopefully be fairly efficient. So I've got a lot of slides that are kind of ready to go. So you won't have to sit there and watch me as I'm using my mouse to do all the writing. Hopefully that'll help make the video a little bit on the shorter side, but also that means that you'll probably need to pause every once in a while to process or maybe catch up with the stuff that I'm writing down. We've got a little bit of Sigma notation to clean up from last week, and then a couple example problems that'll be pretty similar to what you'll see in your homework assignment that's due on Wednesday. And I thought there was something else I wanted to mention, but I guess I'll get right into it starting now. Okay, so the transition from the Riemann sums to where we're going with this integral goes like this. I'll refer to the area under the curve, even though it's really not always the area under the curve. When we do these rectangular approximations for the area, if I have a function that lies below the x-axis, we end up getting these negative areas, base times height. Well, if the height is negative, we end up getting negative regions, and that's okay. When I say the signed area under the curve, I may be referring to an area that ends up being negative. And when we look at velocity telling us something about position, if my velocity is negative, if I'm moving backwards, I want to account for that. If I don't want to account for that, I could do the absolute value and make this function positive and then find the area literally under the curve. But when we're doing these rectangular approximations like you've been doing, like you did in the homework that was due on, well, I guess earlier today on Monday, or yesterday if you're watching this Tuesday, we want to account for that negative area. And the sigma notation, I know it's scary, I know it seems foreign, but the sigma notation is just saying we're adding up a whole bunch of stuff. What are we adding up? Well, we've got the height of the rectangle, that's just the value of the function times the width of the rectangle. And all of these weird subscripts and all this other stuff going on, I know it's a scary looking notation, but all this is adding up the area of a whole bunch of rectangles. So for example, if I'm doing area under the curve y equals x squared between x equals 5 and x equals 10, between 5 and 10, if I'm dividing this up, I'll try to do this fairly evenly. 1, 2, 3, there's a bad job. 1, 2, 3, 4, 5. So here's 5, here's 10. The leftmost interval goes from 5 to 6. So if I'm doing right-hand rectangles, the first place I'm plugging in that x value is at 6. Plug it into the function. Width of each rectangle is 1, so base times height plus base times height plus base times height, where the height is determined by whatever the function is. In this case, I'm plugging in 6, 7, 8, 9, and 10, and the outcome of that, the result of that is the area of that rectangle. In this case, because x squared is increasing on that interval, these would all be overestimates, but like we saw last week, that depends on the type of function. Now, if I change this, and instead of doing 5 right-hand rectangles, if I want to do this with 10 right-hand rectangles, notice that the width of the rectangle has decreased because I have more of them. I've got an interval that is 5 units long, divided into 10 pieces, so each one is half of a unit wide. And now the way I've got this written down, instead of writing 5.5, 6, 6.5, 7, 7.5, etc., since I've got 10 of them, I don't want to write out the whole thing. So I'm establishing a pattern. For this one, I didn't start at 5. I started 1 unit to the right of 5 and then moved up steps of 1. When I have 10 right-hand rectangles, the first place that I'm evaluating this is at 5.5. 0.5 more than my leftmost endpoint, x equals 5. So I'm adding a half once. And then with the next rectangle, I'm adding a half twice. Moving over by a half, moving over by another half, another half, another half. And if I write it in this form, you can see that I'm just adding up a whole bunch of things, starting at x, or at, well, yeah, I suppose, oh no, not x equals 1, but at some counter. Whatever that counter is, I'm adding it once, then twice, then 3 times, and then I keep going until I get up to 10. And this is the height of that last rectangle. If I do it in this form, it's always the same thing. It's a half for the width of the rectangle times 5 plus a half a certain number of times, starting at 1, going up by 1 until I get to 10, which makes it translatable into sigma notation. Width of the rectangle times the height of the rectangle, 5 plus a half. I used Q when I was writing this one up, but you see this as an N, you'll see it as a K, you'll see it as any letter you want, except, well, you probably want to avoid numbers like E and pi and I and stuff like that. But anyway, this is what it looks like in sigma notation. If I do sigma notation, if I'm doing 100 rectangles, well, the work I have to do ahead of time is to say, well, if I've got from 5 to 10, an interval of length 5 divided up into 100 units, each one of those units, each one of those rectangles, each one of those intervals has a width of that, 0.05, 5 divided by 100. So for each one of these, the width of the rectangle, 0.05, and then the place where I evaluate it will be, well, 0.05 times more than where I'm starting this interval, in this case at x equals 5. So that very first rectangle, my left-hand interval starts at 5. And the other side of that first interval is happening 0.05 to the right of that. So yes, it's 5.05, but I'm treating that as 5 plus 0.05 once. The next interval, I'm adding 0.05 again. I'm adding it twice, and then 3 times, and then 4 times, and then 5 times, and I keep going until I get to the very end of this. Yes, it's going to be 10, but in terms of my sigma notation, I'm adding 0.05 100 times. And if you plug k equals 100 into this, you'll get 10. This will be 10 squared. It's going to be 100 times 0.05, the width of that interval. The whole point of this is, first of all, giving us a language that we can talk about this doing something like 100 rectangles without writing 100 terms, and also so that we can get to recognition. And this was some of the questions that were in the assignment that I told you to skip for the assignment that was due, I suppose, technically on Wednesday, Monday, well, whenever that assignment was due that I told you to skip problems from. So that you can take something like this. I want to write in sigma notation what is the area under the curve f of x equals cosine of x between 0 and pi. If my interval is between 0 and pi, dividing up into 10 rectangles, the width of each rectangle is 10 over pi. So there's width of the rectangle. And then the function is cosine of whatever. And the whatever, since we're starting at 0, the first x value that's going to get plugged into this is 0 plus pi over 10 once, and then twice, and then thrice, and 4 times, and 5 times, and 6 times, until we've done it 10 times. And by the time I plug in the 10th time, we'll be at a value of pi. 0 plus pi over 10 times 10 gives us just pi. And then where we head with something like that is that if I generalize and say I'm not just doing it 10 times, but I'm doing it n times, we end up with this expression. Instead of pi over 10 or pi over 100 or whatever, it's pi over n, and we're doing it n times. All of a sudden I've got something, and if you're programming something, if you're programming a calculator, making a spreadsheet, or whatever you're doing with this, you can just change that one variable, and you'll be okay moving on from there. And where we're going from there, and I'm going fairly quickly through this. Honestly, this isn't that big of a deal, but I feel like I want to explain where this is coming from so that when you see sigma notation coming up later on, you'll be okay. You're going to be okay. If you're struggling with the sigma notation, it's almost over. It's going to go away kind of like the definition of a derivative when we were doing derivatives with limits and h's going to 0 and stuff like that. But I'll finish with this by saying that when I have this general form, if I want to move toward exact area instead of an approximation, I don't want 10 or 100 or 1,000, but I want to find the limit as n goes to infinity. I've got this expression in terms of n. I can let n go to infinity, and if I can evaluate this, we can find the exact area under this curve. And in the case of the cosine curve, between 0 and pi, we've got the symmetry. We've got this positive area that would balance out with the negative area. I know the answer is going to be 0. I'm not actually evaluating this limit, doing anything except understanding that this positive area and negative area are going to end up balancing out and giving me a value of 0. This reminds me of a t-shirt that says something like, what part of the limit as n goes to infinity of the sum as k goes from 1 to n of pi over n times cosine of pi k over n don't you understand? Where it ends up just being 0, but it looks like a foreign language. And if it looks like a foreign language to you, that's okay, because we're about to change into integrals. If we let the number of rectangles grow without bound, if we let the size of the rectangles shrink down to 0, this limit notation, this scary, awful limit of a sum notation, becomes this thing called the integral. And this you're going to be much more comfortable with. This is much less scary looking than this limit notation, and it's better. It doesn't give us an approximation. It gives us the exact area under the curve. And we've seen a little bit of this, so I can go fairly quickly through this idea because we've named this stuff already. These are notes that we've seen already. Just to make sure that I've got this formally written for you. Limits of integration, lower limit is usually treated as the left side, the upper limit usually treated as the right side. The actual function we're doing here is called the integrand. We're not going to use that word a whole lot, but when I refer to the integrand, that's just the function that we are integrating. And then finally, dx, it comes from this thing called the differential that we talked about last semester. But for what we care about, and it's actually called the dummy variable, not a term that we're going to use a whole lot, but it just kind of tells us what is the variable here. And this comes into play more when we're in multivariable calculus and you've got multiple variables. What is the one that we're actually integrating in terms of? Usually not a big deal. What I often will tell students is that dx, I'll use the phrase, it's the period at the end of the integral sentence. It doesn't really add to the sentence. I mean, technically it needs to be there. Technically, I suppose it tells us something. I can't, I'm having a hard time moving this around, sorry. This is why I try to have my slides pre-made for these videos. That's what I'm thinking of for the dummy variable. The period at the end of the integral sentence. Mostly it just tells us that we're at the end of the integral. It also tells us what the variable is and stuff like that. All right. The example we did in class, I'm not going to go over this one again, but just to remind you, if we're using Riemann sums, if we're estimating an integral, we're going to do it like we did in class, using your calculator, well, like you did on the quiz also on Monday. But you're finding different values of the function from your calculator, a rectangle times the height, plus the width times the height, plus the width times the height, and you add up all of those rectangles. But what I want to do today is to actually evaluate some integrals, and we're going to get exact values. If I say, what is the integral of x dx from 0 to 5? And I'll say that again. I would read this expression as the integral of x dx between 0 and 5. My function in this case, f of x, y equals x. And that's just this line with a slope of 1 that goes through the origin. So if I say, what is the integral of x dx from 0 to 5, I'm just asking, what is this area? What is the area under this curve between 1 and 5? And for your assignment from this section, it should be geometric shapes that you know the area of. This is a triangle. It's a triangle with a base of 5 and a height of 5. So area is 1/2 base times height. The value of this integral, 1/2 5 times 5, the integral of x dx from 0 to 5 is 12.5. And that's it. We'll see trapezoids. Same function, integral of x dx from 4 to 9. Same idea. And when I've done this one in class, if I was talking with you guys, I would probably say something like, I'm not going to move on to the next one until I hear 3 different strategies for finding area under this curve. And I've certainly seen in the past, someone will say, well, let's find the area of this great big triangle and then subtract away this void down here, this little triangle that's missing. But other people who have said, let's split this up, giving us a triangle on top of a rectangle and just add those two together. Or I've seen people that just say, well, it's a trapezoid. Let's just find the area of a trapezoid, 1/2 of the height times the sum of the bases. Now, some people maybe don't remember that. There's a formula we could use. And then some people will say, well, let's take this rectangle and take away this triangle. And that'll give us that same area. Either way, in this case, when I did this, I do remember the formula for the area of a trapezoid, so that's what I did. 1/2 times the height of the trapezoid times the sum of the bases to get the integral from 4 to 9 of x dx equals 32.5. The integral from 0 to 10 of the square root of 100 minus x squared. Wow, that's a crazy looking one until we realize if we graph something like this, and I think we did something like this last week sometime, that's just a circle. Square root of 100 minus x squared is the formula. I suppose it's technically the top half of a circle. If I'm integrating from 0 to 10, I'm just looking for the area under this part of the circle. And so I would say that the entire area of a circle with the radius of 10 would be pi times 10 squared, or 100 pi. But I'm only looking at 1/4 of that circle. So this is going to be 1/4 of 100 pi. And so this integral will be equal to 25 pi. So anyway, you're going to have some questions from your assignment doing stuff like that, and I'm going to skip. I've got another trapezoid coming up here. There's one where there's an absolute value. Well, if I graph this absolute value function and say find the integral between 0 and 3, I'm just adding up the areas of these two triangles. I'm worried that my video is going to get quite a bit too long if I go through every example. So I think I want to skip to one that's a little bit more complicated. This is one that the writers of the AP test love to put on an AP test in the free response section. Something like this. I've got this function. I remember one year it was the velocity with which a squirrel is running back and forth on a wire or something like that. If I want to find the integral of this crazy piecewise non-differentiable function, it's just finding the area. It's finding the area between x equals -7 and x equals 9. And we're just going to break this thing up into chunks. I've already done that for this one. There's multiple ways you could do this. Again, we could let this area be a trapezoid between x equals 6 and x equals 9. We could take these two regions and say that these two regions would cancel each other out. So I can just kind of ignore this part of it. And that ends up making this other section a little bit more complicated. So I'd probably just leave it as is. Oops. And then I just add them up. I've got a square here. I've got a little triangle with an area of 1 above the axis. I've got a larger triangle with the area of 8 below the axis. So I'm subtracting. That's a -8 going onto this area. Plus 2, the area of that triangle. Plus 16, the area of this square. Plus 2 pi, half of the area of a circle with the radius of 2, etc., etc. And then I'm just adding up all of those areas. When I did this, I got this. The integral of this crazy, complicated piecewise function is 63 halves plus 2 pi. Okay? And then I'll finish up. There's a whole bunch of different properties. I'm going to go through these. I'm hoping to do this in a way that's efficient yet informative. Um, and I'll probably get rid of this notation here, or this note. I'll point out that most of the properties of integrals are true because integrals are just infinite sums. I'm adding up a whole bunch of things. And so a lot of properties of integrals come from just properties of things being added together. Although that's not exactly true for this first one. Let's see. I don't want to delete this. I'll maybe just shrink it down a little bit. I need just a little bit of space here to say that the integral of a constant between x equals a and x equals b, if it's just a constant, that means it's a rectangle with the height of c, and the base of that rectangle is b minus a. Now, I don't want to give you a formula to memorize, but this is just me reminding you that it's just base times height. The height is the value of the function, the integrand, and the height, well, that's just how wide the integral is. Whoops, sorry, the width is how wide the integral is. And so technically, this is a formula. What's the integral from 5 to 7 of 8 dx? It'll be 8 times 7 minus 5. It would be 16. But I'm just thinking of that as a rectangle. Integral of a sum or difference, this is getting along the same lines of if I'm adding two things together, I can change how I add up all the individual pieces, similar to derivatives. If I've got the integral of this thing plus that, I'm allowed to break that up and look at those two integrals separately. This will come in handy when we get to more complicated integrals. We're allowed to break it up. The integral of a constant times a function. Again, similar to derivatives, I can just kind of deal with that constant separately. I can pull that constant outside of the integral and simplify the function that I'm trying to integrate, whatever that happens to be. Just like we could with derivatives. Just ignore that constant. It's not a big deal. It doesn't really enter into anything. We can't forget about it, but we can ignore it as we're doing the more complicated stuff. I'm separating an integral. I'm going to come back to this one in just a second. Before I do that, I'm going to show you graphically what this is saying. If I say the integral from a to b is 8, and the integral from b to c is 3, I ask you what's the integral from a to c, well, we're just adding those two sections together. And that's what that property is saying. The sum of an integral, if I separate that, the integral from a to c is the integral from a to b plus the integral from b to c. We can split that up into two sections, like was on the graph that I just showed you. And then we get into a couple that are a little bit more obscure, reversing an integral, and I'll try to justify why this makes sense on my next slide. If I switch the limits of integration, notice that my upper limit and lower limit, my a and b, are switching places between these two. Turns out that when this happens, if I'm going backwards, the value that I get from my integral is just the opposite of what it was. And the example I like to use is this one. We know, well, at least I think it makes sense for me to say that the integral from a to c of my function, I should have had this one ready to go, is equal to the integral from a to b of the function plus the integral from b to c of my function. And this is true. This is always true, assuming that there's no gaps or weird things going on. But then if I move these boxes out of the way and reveal my axis doesn't go in alphabetical order, this is still true. So in terms of what we're looking at right now, the integral from A to C, the integral, the area under this curve between A and C is 8. The integral from A to B is 11. And here's the question mark. The integral from B to C, well, it's not from C to B. The integral from C to B would be 3. So how do we handle this if my upper limit is lower than my lower limit? And so this is where that definition comes from. If I change my limits of integration, well, we got to fill in the blank here. 8 is equal to 11 plus what? Well, in order for this to make sense, this number needs to be the opposite of the integral from C to B. The integral from B to C must be the opposite of the integral from B to C in order for this to make sense, in order for this to be consistent with what we already learned. And so, if I've got this example and I give you a couple different things, and I ask, what is the value of the integral from 0 to 6 of the function? Well, I've got this positive 4 here. I've got this negative 22 area here. So I'd have 4 minus 22. This would give me negative 18. And so if the integral from 0 to 6 is negative 18, the integral from 6 to 0, well, that must be positive 18. If I switch the limits of integration, the value of the integral is the opposite. And then if I say, what's the integral from 6 to 2 of f of x? Well, let's see. The integral from 2 to 6 would be negative 22, so this must be positive 22, the opposite of the negative 22. And there are quite a few examples of problems that you'll do in the assignment. I'm just going to take a peek. Yeah, we don't want to take a look at what's on that next slide. But using a lot of these properties, getting you used to this. I'll be honest, this assignment's going to be a little bit of a struggle because we're speaking a new language. This language of integrals is it's certainly not something that we're used to. So I'm going to suggest, and this maybe doesn't apply to everybody, but you might want to watch this video again, if for no other reason, to hear me use these terms and to hear me describe things and refer to different things in hopefully a way that becomes more clear as you see them more often. And then, of course, look at the section in the book. Don't just go straight from this video to the problem set. Look at the examples that they've got. Look at the worked out problems that they have in this section. That's going to be helpful. And then, of course, when you see me on Wednesday, we should have some time. If there's some questions that you have, I want to make sure that we're okay with this stuff before we move on. So there we are. I'm going to wrap this one up. This video is already long enough as it is. Hopefully this is helpful, maybe even more helpful if you watch it more than once.